Hello, and welcome to Linear Algebra. This is lecture 13, and our topic is error correcting linear codes. Okay, so last time we talked about subspaces associated to linear transformations. Right, namely the kernel or null space and the image or range. This time, it's a rather different topic. We're going to be detecting and correcting errors in codes. Okay, so the idea is to think about data transmission. You have, for example, Wi-Fi, and you have some data that you're trying to transfer from one place to another, and for many reasons, computer error, or interference, or just noise, you can have what one person receives be different from what another person meant to send or sent. So what we want to talk about are ways of noticing that this has happened, and even better, trying to automatically correct and recover the original message, even from corrupted data. Okay, so let's start with some definitions. So a binary code, this is going to be the message. So we're going to think of it as a subset of some power of F2. So that's what makes it binary, that we're working with F2. So it's the zeros and ones. And, well, sorry, let me spell this out a little more. It's a subset of F2n for some n. Okay, and then an encoding function is a bijective function from F2k to C. Okay, so what you want to think is that here are the words that you want to send, right? I mean, word, it's a string of zeros and ones, but we're going to think of it as a word. So you have the message you want to send. And to send it, what you do is you encode it using this function f into your binary code. So we can think of C as the code words. Which get used instead of the original chunks of data in F2k. All right, so you don't want to send your bank password directly through the internet. You encode it first into a code word, and then that's what you transmit. Right, so F tells us which code word represents each piece of data. So for example, like in the bank password example, F might be encrypting the data. So we would store f of x1 through f of xm code words instead of storing x1 through xm. That way, if somebody, a bad actor gets access to the data, they would just have the code words and not the original message. So notice that it's crucial that f be injective, right? Certainly you want different pieces of data to have different code words, right? If two pieces of data had the same code word, then knowing the code word would not tell you what piece of data you had meant to store, right? That is to say, otherwise we would lose data. When we were encoding. Okay, now since we're in a linear algebra class, we want things to be linear. So let's modify the definition. We'll say that a binary linear code is a subspace C of F2n, and a linear encoding is a bijective linear map T from F to the K to C. Right? As you'll recall, bijective linear maps are also called isomorphisms, linear isomorphisms. So that's what we have to encode messages. We're going to assume that our encoding is linear and that our codes make up a subspace. So we can think of T as a linear map from F2K to F2N with range, image, being this subspace of code words. And of course, an advantage of thinking of T as a linear map between powers of F2 is that then it is represented by a matrix. It's given by multiplication by a fixed matrix. Right, so we have a matrix A of size n by k with entries in F2 called the encoding matrix. Right, so directly from its definition, A satisfies that its kernel is equal to 0, right? Because we saw last time when we were talking about the kernel of a linear transformation that a linear map is injective precisely when its kernel is equal to 0, the 0 vector. And C is the column space, right? The image. Okay. So let's think about how things might work in practice, right? So suppose Alice has some data. right? And this data is put into binary. So it's converted into a bunch of zeros and ones. K zeros and ones. Which she encodes as the vector y just by multiplying x using the matrix A. And so ends up with a vector F2n. Right, so it's standard that you'll end up with a longer message after you've done the encrypting, right? Because you want to have all of the initial data and then some extra data there, either for encryption or, as we'll see in a moment, to worry about errors. So what would happen is after Alice encodes the message, she transmits Y to her friend Bob. It's very common when discussing this sort of thing that you have Alice and Bob as the ones who are sending and receiving messages. So in this case, she sends it to Bob, who receives Z. Right? So Bob might not get exactly what Alice transmitted, right? Because again, something could have happened to the data in between, right? There could have been some noise, or some corruption, or some interference, or even a malicious actor changing some of the data. So we can think about the two settings. So if everything works, properly, then C is equal to Y. Bob just gets exactly what Alice transmitted. So then Bob uses A to recover the original X, right? Because Bob receives Y and Bob knows the matrix A. So there is now a system of linear equations to solve, and Bob knows all about Gaussian elimination. So there's no problem from here finding the original X, right? And because we know that the kernel of A is just a zero vector, when Bob solves this system, there is a unique solution. So Bob finds X. Right, but if something goes wrong, Bob will get some other vector Z, different from Y. So it would be good if Bob could tell that he had received the wrong vector. Right? Even if Bob can't fix it, it would be good for Bob to know that something went wrong. Okay, so for example, maybe what they do is, Alice is going to send something, K bits, and a very simple thing that Alice could add is, let's say you just take those K bits, they're all elements of F2, and you just add them up, right? So you end up with a 0 if there were an even number of ones, and you end up with a 1 if there were an odd number of ones in the message you wanted to send. So Alice could just add one more bit to the message that's either a 0 or 1, whatever the sum of those was. And so then Bob could just check, okay, well, is the last bit equal to the sum in F2 of all of the previous bits? And if not, then he knows that something went wrong. Okay, so we're going to say that a linear encoding with an encoding matrix A is error detecting if, okay, so error detecting. So here's what we want to think. In this example of just adding the things up, if only one bit got changed, Bob would know, right? Because if one bit changed, then the sum of the first k bits is not going to be equal to the last one, right? Because changing one bit would change the sum. So that's good. That's good. That means that you would be able to tell if something went wrong. So in general, we want to think that that only one bit goes wrong, right? So we're thinking that randomly, if we have a good transmission channel, then it's unlikely that anything goes wrong. And so it's even more unlikely that two things go wrong. So we're going to not worry about things getting too corrupted. We're just going to focus on the most likely bad situation, which is that one bit goes wrong. Okay, so we're going to say that a code is error detecting if it'll notice when one bit goes wrong. Right? So here's how you want to phrase that. So we're going to say that whenever you have a code word, so this is something that you want to send, and C is something else in the things that Bob might have received. And they differ in exactly one place. To exactly one entry. Then Z is not a valid code word, right? So if you have a valid code word and you mess it up in one spot, then you don't have a valid code word. And so you can recognize, in principle, that the thing you got is not what Alice meant to send, right? Because it's not a valid code word. Okay, so then, well, then you want to check if this happens. So we're going to say that a parity check matrix is a matrix capital B, size m by n for some m, with entries in F2, such that the kernel of B is equal to the column space of A. Okay, so how would you use a parity check matrix? So it's called parity check because of the example I just gave you, where you're just checking how many ones, Alice counts how many ones the message had, and just includes one more bit with a 0 if there were an even number and 1 if there were an odd number. So here's what would happen. So when Bob receives Z, he computes B times Z, right? He wants to know if Z was a valid code word. Valid code word means that you're in curly C, which is the column space of A. So he wants to know, is Z in the kernel of B? Right? So if Z is not in the kernel of B, then Bob knows that some error occurred. Okay. So how are parity check matrices related to error detecting codes? Well, here's one way of telling that you have an error detecting code. If a linear encoding has a parity check matrix whose columns are all non-zero, then the encoding is error detecting. Okay, so let's prove this. So, okay, we want to prove, we're going to assume that we have a linear encoding with a parity check matrix whose columns are all non-zero. All right, so let A be the linear encoding. Matrix, and B, a parity check matrix whose columns are all non-zero. Okay, we want to check that this encoding is error detecting. Right, so assume Y is a valid code word, and Z Z is an F2N differs from Y in one entry. Okay, then Y, so we could write it like this, C, okay, if Z differs from Y in their jth entry, then Zi is either equal to Yi if I is different from J, or it's Yi plus 1 if I is equal to J. Let's go ahead and say Yj plus 1. Right, because in Z2, in F2, the field with two elements, I can toggle between 0 and 1 just by adding 1, right? So if Yj is equal to 0, then this gives me 1, whereas if this was equal to 1, then this gives me 0. Right, so I know that Z, the vector Z, is equal to the vector Y plus Ej. Right, because all I need to do is add 0 everywhere except for the jth entry where I add 1, and that's exactly what the coordinates of Ej are. Okay, so now let's do B times Z. Yes. B times Z, this is equal to B of Y plus Ej. This is B of Y plus B of Ej. And B of Y is equal to 0. This is equal to 0 because Y is a code word, right? And an error error detecting, a parity check matrix vanishes on all valid code words. So B of Y is equal to 0. This leaves us with just Bij, and we know what Bij is. This is equal to the jth column of B. And by assumption, all of the columns are non-zero, so this is not equal to 0. Hence, C is not a valid code word, and that's what we needed to check. Okay, so there we go. We've shown that if you have a linear encoding and it has a parity check matrix whose columns are all non-zero, then that encoding is error detecting, right? If you have a valid code word and you switch it in one spot, it's no longer a valid code word. Okay. So perfect. So now in this situation, Alice sends a message. Bob uses his parity check matrix and notices that something went wrong. Well, then Bob could let Alice know that something went wrong, and Alice could send it again, and then Bob could hope that this time it doesn't go wrong, nothing goes wrong. But of course, it would be much better for everybody if Bob could tell not just that something went wrong, but also what the correct message would have been, right? If Bob can fix the error, right? Remember, we're assuming things only went wrong in one spot. So it would be great if Bob could just find that spot and fix it. Okay, so we're going to say that a linear encoding right, with encoding matrix A is error correcting if, okay, so let's say that you're in the situation where you have a code word, and then you have Z that differs in one spot. Okay, so we're in the situation where Alice sends something, something goes wrong, Bob receives something that's different from what Alice sent, but it's only different in one spot. We're going to say that it's error correcting if that's enough information. Z is enough information for Bob to find Y, right? So how could it possibly be enough information? Well, if Z is close to Y, but not close to any other code word, right? So we're going to say, whenever this happens, Z differs from all other elements of our codebook in at least 2 entries, 2 digits. Let's say entries. Okay, so it's going to be error correcting if whenever Bob gets something, Bob can tell what Alice meant to say. Right, okay, so how could something like that work? So a simple example is the triple repetition code. Okay, so in this code, if Alice wants to send a single digit, Alice just takes this digit and repeats it 3 times, right? And sends that. So if Alice wants to send 0, Alice would send 0, 0, 0. If Alice wants to send 1, Alice would send 1, 1, 1. Right? So in terms of our notation from before, if x is equal to 0, then y is equal to 0, 0, 0. And if x is equal to 1, then y is equal to 1, 1, 1. Okay, so now Bob might not get exactly what Alice sent, but we're assuming that if things go wrong, they only go wrong in one spot. That means that if Alice sends 0, 0, 0, Bob might get 2 zeros and a 1, right? But if Bob gets 3 zeros, or 0, 0, 1, 0, 1, 0, 1, 0, 0, he knows that Alice transmitted 0, 0, 0, right? Because only one bit couldn't go wrong. by assumption. We're assuming only one bit can go wrong. So if they agreed that this was the code they were going to use, then any of these can be repaired to 0, 0, 0. And recover x equal to 0. Okay, so in this case, the encoding matrix is 1, 1, 1. Right? So if you multiply this with the 1 by 1 vector 0, you get 0, 0, 0. If you multiply this by the 1 by 1 vector 1, you get 1, 1, 1. Okay, so it's column space. And so this is, of course, all of the y's in f2 cubed, such that y1 is equal to y2 is equal to y3, right, which is exactly our codes. Okay, so let's come up with a parity check matrix. A parity check matrix B needs to satisfy that the kernel of B is the column space of A, right? It's the column space of A, which is, as we just noted, all of the y's in f2 cubed such that y1 is equal to y2 and, well, so y1 is equal to y2 equal to y3, which we could write as y1 is equal to y2 and y2 is equal to y3. And I want to write it like that because then I can also write it as y1 plus y2 equal to 0, y2 plus y3 equal to 0. Remember that in the field f2, minus 1 is equal to 1. So if I want to write y1 minus y2, this is the same as writing y1 plus y2. Okay, so now I just need a matrix B whose kernel consists of those vectors in f2 cubed satisfying, whose coordinates satisfy these two equations. So that's easy. Put 1, 1, 0 and 0, 1, 1. Right, so 1, 1, 0 gives me this equation and 0, 1, 1 gives me this equation. So this matrix works. Okay, so for this encoding, we found a parity check matrix. And notice that this parity check matrix shows that it is error detecting because all of the columns are non-zero. Okay, now in fact here, not only are they all non-zero, but they are also distinct, which is good. Which is good because in fact, when you have a parity check matrix like that, you can tell that your code, your encoding, is error detecting. So if an encoding has a parity check matrix B, whose columns are all distinct and non-zero, then it is error correcting. Okay, and this is easy to check now because we can argue very similar to the previous proof. So as before, we would have C is equal to Y plus EJ, right? If Y is a code word and Z is something else that differs from the code word in exactly one bit, in this case in the jth spot, then we saw that b times z is equal to b times ej, which is equal to the jth column of b, right? But since the columns of b are distinct, this tells us what j is. And we can recover y as z plus ej. Right? So this is error correcting. From the corrupted data, Bob can find the uncorrupted data, right? Because Bob receives z, so Bob computes b times z, and that turns out to be one of the columns of b. But which column tells Bob which digit of y got corrupted? So Bob just fixes that and finds y. Okay, so this leads to an idea due to a guy called Hamming, which I'll tell you more about at the end of the class. But this leads to the idea that you should just make B as large as possible, right? To make the most efficient error correcting code, what you want to do is make B as large as possible. Right, so for a given M, take as columns all non-zero distinct vectors in F2 raised to the n. So for example, for m equal to 3, we take, okay, so I'm going to construct this matrix B. The columns are going to be elements of F2 cubed. So I'm going to have 3 elements in F2. There can be either 0 or 1. And I just want to choose all possible distinct choices. So, okay, 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0. Right? Those are all possible distinct non-zero vectors in F2 cubed. Right? So we end up with a matrix of size 3 by 7 in F2. Okay, so this is going to be the parity check matrix. And then we want to find a matrix A to work with this. Actually, let me change the order of these 2 vectors, just so I don't mess things up later. Okay. So having chosen B, we then need an A, right? So we know that it has to be of size k by 7 for some k, right? So this k is going to be how many bits we're able to encode. Our message is going to have length 7, right? That length comes from the size of our parity check matrix. And what we want, right, these matrices will be compatible if, right, the kernel of B is exactly the column space of A, right? So our code words are exactly the kernel of B. So here's a way of finding such an A. So if we write B as a partition matrix, say M and then I3. So here you notice that we have the identity matrix at the end. So here the matrix M is just everything before that. So 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1. Right, notice this is of size 3 by 4. And then we can set A to be the identity matrix over M like this. So this would, you would put a 4 by 4 matrix here, and then you would put this matrix right underneath it. Right, so to be explicit, so this would be 1, 0, 0, 0, and then 1, 1, 1, and then 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, 1, 0, 1, and then 0, 0, 0, 1, 0, 1, 1. And we end up with a 7 by 4 matrix. Then the kernel of A is equal to 0, right? That's easy because if you have a linear combination of these columns equal to 0, then just looking at the first 4 entries, you'd be able to see that all of the coefficients have to be 0. So you started with the 0 vector. And B times A is defined, right? So the sizes work out so that this product makes sense. And it's given by, so it turns out to be easy to compute. Using this partition of the matrices, we end up with M times I4 plus I3 times M, which is just M plus M, right? But because we're working in the field F2, M plus M is just the 0 matrix. Okay, but if you have this product equal to 0, that tells you that everything in the image of A is contained in the kernel of B, right? And that almost shows what you want. In fact, I'll let you check or read in the book. There is an equality here. The column space is equal to the kernel. Okay, so how would this work in practice? So if Alice has a message with 4 bits, then she transmits Y, A times X, which has 7 bits. And Bob receives C. Let's say that it got corrupted, and so it's Y plus EJ. Okay, so then Bob computes B times Z, which, as we've seen, is B Y plus EJ, B Y is equal to 0. Right, so I'm just repeating here. And this is the jth column of B. This tells Bob there was an error in the jth bit. And so Bob knows that Y is equal to Z plus EJ and can use A to find X. Okay, so then Alice only needs to transmit 7/4 as many bits as in the original data, right? And so you can see that this is better than our first naive attempt, right? The triple code. Because if we were to use the triple code, then if Alice wants to transmit k bits, Alice needs a message of length 3k, right? And now with Hamming's idea, Alice only needs to transmit 7/4 k bits. Okay, so but you see in this recap that as long as the transmission can only get messed up in 1 bit, then Bob is always sure to find the original X, and so to get the information that Alice wanted to send. Okay, so great. So next, let me give you some historical context on this. So in particular, mention Richard Hamming, who it's nice to note actually got his PhD from UIUC, 1942. So Richard Hamming, who was alive from 1915 to 1998, wanted to be an engineer initially, but because he was going to college during the Great Depression, he could only get a scholarship to Chicago. And Chicago didn't have an engineering school at the time. He ended up being a math major instead. He got his PhD from UIUC in 1942, and then went to work at Los Alamos on the Manhattan Project, so constructing the nuclear bomb. At Los Alamos, he worked on the IBM calculating machines. His wife, Wanda Hamming, but named Little, worked as a human computer, right? So as you've no doubt heard, before digital computers, there was a profession of computer, and it was often done by women. I encourage you, if you haven't already, to read Hidden Figures by Margot Lee Shetterly on the early space program. Or if you like sci-fi, or I guess this would really be a combination of alternate history and sci-fi, there's a wonderful series of books by Mary Robinette Kowal called the Lady Astronaut series that envisions having to go to space, this human race needing to get into space, but before the digital computers invented. And so women go along as human computers, among other things. So there's a fun story about when Hamming was at Los Alamos, one day he gets asked by a physicist if he would please check some computations over the weekend. And Hamming said sure, but initially was thinking of giving the job to somebody else because his time was too valuable to be spent just checking some computations. But he asked, what is it that you're computing? And the physicist explained that he wanted to compute the probability that the test of the nuclear bomb that they were going to do the next week, how likely is it that that would set the entire Earth's atmosphere on fire? So Hamming decided that that was probably a computation he would like to check himself. So he did, and it turned out okay. After he left Los Alamos, he went to work at Bell Labs. And then he had the experience of starting a code running on a machine on a Friday, coming back on Monday, expecting the machine to have done the computation over the weekend, and finding that, in fact, the machine had stopped very soon after he left on Friday because there was an error of 1 bit. And there was a parity check that let the computer realize there was an error, but Hamming realized that it would have been much better if the machine had just been able to correct the error itself on Friday instead of sitting idle all weekend waiting for him to come back on Monday and have to correct the error and then restart it. So that's what inspired him to work on error correcting codes. Yeah, excellent. So he worked there until 1976. He retired and worked as an instructor at several universities until he died. He died very soon after becoming an emeritus professor. Okay, very good. We'll stop there and pick it up from there next time.